In this module, we will study the 2-position and 3-position synthesis problems for 4-bar mechanisms. Let us look at the 2-position synthesis problem first. Given 2 positions or poses of the coupler, which is shown in this picture at E1 and E2, our goal is to design a 4-bar mechanism that ensures that the coupler reaches the poses E1 and E2. And we also want to design an input diode that ensures that the coupler motion is limited between the poses E1 and E2. If you recall, we have solved this same problem using graphical synthesis before. For graphical synthesis as well as for analytical synthesis, the problem 2 or the input diode design problem, once the problem 1 has been solved, is same as the crank rocker mechanism synthesis problem that we had studied earlier. Therefore, we will focus on solving the first problem. And again, here the procedure that we will be using will mirror the graphical synthesis procedure closely. First, let us understand the meaning of given 2 positions or poses. Let's call these 2 points A1 and A2. So the point A is where I have attached a locally rotating coordinate system to the coupler. When it is said that the pose of the coupler is known, it means that I know the vector OA, which means I know this length R1, this angle θ1, and I know the angle, the x-axis of the LRCS makes with the x-axis of the global frame, which is alpha1. Similarly, I know the pose E2, means I know the position of A2, which I will denote by R2 and θ2, and I know the angle alpha2. Now the problem 1 can be restated as design 2 moving pivots on the coupler and 2 fixed pivots such that the resulting 4-bar mechanism ensures that the coupler reaches poses E1 and E2. And as we had done before, our strategy will be to select or choose the 2 moving pivots on the coupler and then compute the position of fixed pivots. In the case of graphical synthesis, we used a geometry construction procedure to find the position of the fixed pivots. In analytical synthesis, we will use algebra and trigonometry to find the position of the fixed pivots. So our goal is to choose 2 pivots, say C1 and D1, and they will be C2 and D2 at the second pose, and to construct O2 and O4, which are the fixed pivots, so that my mechanism is O2, C1, D1, O4. Note here that the moving pivot C will always lie on a circle with center at O2, and the moving pivot D will always lie on a circle with center at O4. So the location of the fixed pivot O2 depends only on the choice of C, and the location of the fixed pivot O4 depends only on the choice of D. Therefore, I can decouple the whole design problems into 2 separate subproblems, choosing C and computing O2, and then choosing D and computing O4. As you will see that the procedures to obtain O2 and O4 are identical once we have chosen C and D. Therefore, we'll first concentrate on showing how to compute O2 given that we have chosen C. This is what is summarized in this sentence here, that given the 2 configurations U1, E2, which basically means this R1, which is the length of OA1, θ1, the angle OA1 makes, R2, which is the length of OA2, the angle θ2, the angle alpha1 here, and the angle alpha2. We want to select the moving pivot C and then determine the corresponding ground pivot O2. As we have already shown, we first set up a fixed frame XOY, which is shown here, and then select a LRCS or a locally rotating coordinate system with origin A, which is shown here. And as I've already discussed, R1, theta 1 and the angle alpha 1 is known, which gives my first pose U1. So when I select the moving pivot, what I do is select it in the locally rotating coordinate system, because in the LRCS or locally rotating coordinate system, the description of the moving pivot or the parameters that describe the moving pivot, they do not change. We use the polar coordinates p and gamma, where p is the length of the vector a1c1 and gamma is the angle the vector a1c1 makes with the x-axis of the locally rotating coordinate system. And these two parameters define the point C. We know that OC1 equals to OA1 plus A1C1, and OA1 is R1 e to the power of j theta 1 because the length of OA1 is R1 and the angle OA1 makes with the x-axis is theta 1. Similarly, A1C1 is P e to the power of j alpha 1 plus gamma because the length of A1C1 is P and the angle that A1C1 makes with the x-axis of the global frame or GCS is alpha 1 plus gamma. Now note that R1, theta 1 and alpha 1 are known because the pose U1 are known. P and gamma are known once we have made the choice for the moving pivot C. Therefore, OC1 is known. Now we will try to determine the moving pivot at the second pose, which is E2. So C2 is now the position of the moving pivot at the second pose. And again, OA2 is R2, this angle is theta 2, and this angle here is alpha 2. Now note that A2C2 is given by P and gamma. Length of A2C2 is equal to P. And the angle that A2C2 makes with the x-axis here is gamma. This doesn't change because, as I said, the description of the point C with respect to the LRCS never changes. Therefore, using similar arguments that we did in the previous slide, that is OC2 equals to OA2 plus A2C2, and noting that OA2 is R e to the power of j theta 2, so this is OA2, and A2C2 is P e to the power of j alpha 2 plus gamma. This is A2C2. So I have OC2 is R2 e to the power of j theta 2 plus P e to the power of j alpha 2 plus gamma. Again, since the pose E2 is known, I know R2, theta 2 and alpha 2. Since I have chosen the moving pivot, I know P and gamma, so OC2 is known. Once I know the moving pivot in the two poses, I know that the fixed pivot has to lie on the perpendicular bisector of the line joining C1 and C2. And you have seen before how to write down the equation of this perpendicular bisector. And you have seen two ways of writing down this equation. We will use the first way. What we will do is first get the position vector OM, where M is the midpoint of C1, C2. So OM is OC1 plus OC2 by 2. And then we know that the equation of this line on which the pivot O2 will lie is given by OM plus K times a vector along this line. And the vector may be in any direction, either in this direction as I have shown here or in the other direction. It doesn't really matter. Now a vector along the perpendicular direction to C1, C2 is J OC2 minus OC1. Therefore, OO2 is OM, which is OC1 plus OC2 by 2 plus J times OC2 minus OC1 times K1. I know OC1 and OC2. Therefore, by choosing a value of K1, I can find one of the fixed pivots O2. Any point on this line can be theoretically used as a ground pivot. However, after we construct our mechanism, we have to check for Grashof criteria and transmission angles, and whether it is possible to continuously move between E1 and E2. So although any choice theoretically serves as a correct choice, in practice we will have to iterate to get the best possible choice. As I said before, to compute O4 corresponding to the other moving pivot D, the procedure is identical. So what we will do now, we'll choose another moving pivot, which is D in this picture, and we want to find the perpendicular bisector of D1, D2. My poses are the same as before. So the magnitude of OA1 is R1, magnitude of OA2 is R2, the angle that the vector OA1 makes is θ1, angle vector OA2 makes is θ2. The orientation at E1 is alpha1 and the orientation at E2 is alpha2. Now the point D that I have chosen is different. So the magnitude of the vector AD, which is same at the two poses, so A1 D1 and A2 D2 is Q, and the angle that the vector makes with the x-axis of the LRCS is chosen as phi. So repeating the same procedure as before, my OO4 now becomes OD1 plus OD2 by 2 plus J times OD2 minus OD1 times K2. I choose any value of K2 and I get the fixed pivot O4. And to remind ourselves, OD1, OD2 are both known, and we can compute OD1 by saying that OD1 is OA1 plus A1 D1. So if you look at the triangle here, OD1 is equal to OA1 plus A1 D1. OD2, which is this vector here, is OA2 plus A2 D2. Since OA1, OA2, A1 D1 and A2 D2 are known, or in other words, R1, θ1, alpha1, R2, θ2, alpha2, and Q and phi are all known. Therefore, OD1 and OD2 are known, and I can compute O4. Since we have already chosen the moving pivots C and D, after computing the position of the fixed pivots O2 and O4, we have the entire design of our mechanism. We can get all the link lengths from the coordinates of the four pivots. As we have discussed multiple times before, once we design a mechanism, we need to check the quality of the mechanism. First, we will check whether the mechanism is Grashof or not. Then, we'll check the transmission angle of the mechanism. And then, we'll also check whether the mechanism can move between the two poses E1 and E2 continuously. The final check can be done using a simulation software or a CAD software, and also by building models. We will now look at the three-position synthesis problem with prescribed precision points. Given three positions of the coupler E1, E2, E3, which are shown on the picture on the left, we want to design a 4-bar mechanism that ensures that the coupler reaches the poses E1, E2, and E3, and we want to also design an input diode that ensures that the coupler motion is limited between the poses E1 and E3. The second problem is a crank rocker mechanism synthesis problem for a prescribed range of rocker motion, which we have tackled in Module 2. So that technique can be used for solving the second problem here. We will focus here on solving the first problem. The problem 1 can be rewritten as the design of two moving pivots on the coupler and two fixed pivots such that the resulting 4-bar mechanism goes through the poses E1, E2, and E3. And as we have stated multiple times before, our strategy will be to select two moving points on the coupler and compute the position of the fixed pivots. Now note again, once I choose the moving pivot C, the fixed pivot O2 is determined. Similarly, once I choose the moving pivot D, the fixed pivot O4 is determined, and my mechanism will be O2, C1, D1, O4. Therefore, the problem of computing O2 and O4 can be thought of as two decoupled problems, and as we will see, the same procedure can be used for both the problems. First, we will look at how to compute O2. We will first set up a fixed frame XOY and select a locally rotating coordinate system with axes small x and small y. We know that E1, E2, E3 are known configurations. E1 is known means that the length of the vector OA1 is known, which we denote as R1. The angle θ1 that OA1 makes with the x-axis is known, and the angle alpha1 which the x-axis of the LRCS at position E1 makes with the x-axis of the GCS is known. Similarly, E2 is known means OA2 is known, which is R2 here. The angle θ2 is known, and the angle alpha2 is known. And the same is true for the pose E3. When you select or choose the moving pivot C, it means that we choose the polar coordinates of the point C, which is P and gamma here. P is the length of A1C1 and gamma is the angle that the vector A1C1 makes with the x-axis of the LRCS. And this P and gamma stays the same for each pose E1, E2 and E3. I can write OC1 equals to OA1 plus A1C1. Similarly, I can write OC2 equals to OA2 plus A2C2 and OC3 as OA3 plus A3C3. The previous three equations can be written compactly as OCI equals to OAI plus AICI, where I varies from 1 to 3. OAI is Ri to the power of j theta I, and AICI is P to the power of j alpha I plus gamma. You can verify it for the pose E1. OA1 is R1 e to the power of j theta 1, and A1C1 equals to the length of A1C1, which is P, and this angle is alpha 1 plus gamma, so it is P e to the power of j alpha 1 plus gamma. Now in the subsequent slides, we will make the notation a little bit more compact. Instead of writing OCI everywhere, we will replace OCI simply by CI. C1, C2 and C3 are the position of the same moving pivot at these three different configurations E1, E2 and E3. Since the moving pivot C will always lie on a circle that is centered at the fixed pivot O2, C1, C2, C3 lies on a circle. Therefore, O2 lies on the perpendicular bisector of C1, C2, and O2 also lies on the perpendicular bisector of C2, C3. The perpendicular bisector of C1, C2 can be written as G minus C1 plus C2 by 2 dot C1 minus C2 equal to 0. If you recall, this is the second way in which we wrote down the equations of the perpendicular bisector in the first module of this lecture, where G is OO2 or any point on this perpendicular bisector. In this picture, I have shown one point which is here. Note that this is just a representation. The actual fixed pivot may not be here. In fact, in this case, the actual fixed pivot is somewhere here. But any point on this perpendicular bisector will satisfy this equation. And as we had seen, if we do this dot product, what you will get is C1 minus C2 dot G equals to half C1 dot C1 minus C2 dot C2. And just remember that C1 is the same as OC1 and C2 is the same as OC2. The vectors OC1 and OC2, which we already know because we know the poses and we have chosen the pivots. Since C1, C2 and C3 lies on the circle, therefore the fixed pivot also lies on the perpendicular bisector of C2, C3 or C1, C3. We can choose any one of them. Choosing the perpendicular bisector of C1, C3, we can write the following equation. C1, C3 dot G equal to half C1 dot C1 minus C3 dot C3. So what we have is two equations in two unknowns. G is the position of the fixed pivot, so it will have two unknown coordinates. In Cartesian form, the coordinates will be gx, gy. In polar form, it will be magnitude of the vector g and the angle the vector makes with the x-axis. So we'll now see how to solve equations of this form for g. Here I have just written down the equations from the previous slide. Now I want to convince you that these equations are actually a set of linear simultaneous equations in the coordinates gx and gy of the fixed pivot O2. To see this, note that C1, C2, G, C3 are all complex numbers. So let us write G as Gx plus JGy, with Gx being the real part and Gy being the complex part. Now C1 minus C2 is a known complex number because C1 and C2 is known. So I write C1 minus C2 with a real part H2x and a complex part H2y, and I call C1 minus C2 the complex number H2. Similarly, H3 is C1 minus C3 with real part H3x and complex part H3y. On the right hand side, here I have C1.C1 minus C2.C2. I call this F2. This is a scalar because dot product between two vectors gives a scalar. So this is a scalar real number. F3 is half of C1.C1 minus C3.C3, which is also a scalar. And both F2 and F3 are known quantities because C1, C2, C3 are known quantities. So with this new notation, this system of equations become this system of linear equations. H2xgx plus H2ygy equals to F2 and H3xgx plus H3ygy equal to F3, with my unknowns as gx and gy, and all the coefficients and the right hand side is known. And you can solve for gx and gy. To compute the other fixed pivot O4, we have to follow the same procedure. We just have to choose another moving pivot D. So we can choose the moving pivot maybe somewhere here, which we call D1. This is our A1. The length of A1 D1 is Q and the angle will be phi. So we'll have OD1 equals to OA1 plus A1 D1. And OA1, the length of OA1 is R1. The angle OA1 makes is theta 1. So OA1 is R1 e to the power of j theta 1. Alpha 1 is the angle here. So A1 D1 is Q e to the power of j alpha 1 plus phi. So I have OD1 as R1 e to the power of j theta 1 plus Q e to the power of j alpha 1 plus phi. I can do the same procedure and get OD2 and OD3. In general, this is the equation that I will have, where I is 1, 2, and 3. Again, you should convince yourself that I know all the ODIs because I know all the RIs, theta i's, and alpha i's by knowing the three poses E1, E2, E3. And I have chosen the fixed pivot D, so I know Q and phi. As you can see, this is the same equation as we had before, with only that I have replaced Ci by Di. So I have to just use the same procedure to solve the problem. So the system of equations that I get will be of this form. And again, you can see the only change that I have here is all the Ci's becomes Di's. And now my definition of G is a little bit different. It is the position of O4. All the other definitions here are identical, and so this system can be written as, again, as two linear systems, and I can solve for gx and gy. So I can also obtain the fixed pivot O4. And again, after I have obtained O2 and O4, because I have chosen C and D, the moving pivots, I know the lengths of all the links, and I have to go through and check whether the Grashof criteria is satisfied, determine the transmission angles, and also simulate the mechanism to make sure that I can move between the three configurations E1, E2, E3 continuously.